Alright, let's look at the homework 14, problem number 1, part A. Alright, so we want to use the power series to find the solution of this differential equation. Alright, so let's do that. Alright, so plug in power series into the equation. Alright, so you have a quantity x squared minus 1. Alright, y double prime would be summation n goes from 2 to infinity. Then you have n times n minus 1 cn x to the n minus 2. Right? Then you have 4x times summation n goes from 1 to infinity n cn x to the n minus 1, and plus 2 times summation n goes from 0 to infinity cn x to the n is equal to 0. Alright, so let's multiply out. So I'm going to put the x squared inside, then you end up getting, so this is going to be equal to, it's going to be, so x squared here, so it's still a summation, goes from 2 to infinity. Then you have n, and n minus 1, cn. But if you multiply by x squared, you have x to the n, which is kind of convenient. And you have a multiply by negative 1, so it's going to be minus summation n goes from 2 to infinity, right? N and n minus 1 x to the, oh actually I forgot the cn x to the x minus 1, right? So we're going to put the 4x inside, so you have plus summation n goes from 1 to infinity, right? 4 n cn x to the n, because you have x here, so that'll make it x to the n, and plus summation n goes from 0 to infinity and 2cn x to the n, right, is equal to 0, right? So we have to make some adjustments. So we want everyone to have x to the n, right? So here we have x to the n, we have x to the n. Right, this one we're gonna have to do a little, actually, let's see. Oh yeah, this one we actually, I messed it up here. Sorry. This is supposed to be n minus 2, right? Right, so we have to make an adjustment here. So what we do is we're gonna do a little bit of shifting, right? So instead of starting from 2, we're gonna start from 0, right? So turn that into 0, right? So if you decrease the starting number by 2, we can compensate it by increasing the indices by 2. So this becomes n plus 2, right? Then this becomes n plus 1. Then you have a cn plus 2, then x to the n, which is nice, so that we have the x to the n, right? And here we already have x to the n, we don't have to do anything, right? Next thing we need to do is we want to start from 0, right here. Look, we can just change that to 0, which would not affect the summation, because when n equals 0, term is 0, n equals 1, term is 0. So adding the first 2 terms are adding 2 zeros. So there's not going to affect the sum. And this already starts from 0. This one, for the same reason, if you change that to 0, when n equals 0, the term is 0 again, so adding a 0 doesn't change the summation. So, and this one already starts from 0, right? So what you get is, right, so everyone starts from 0. So n goes from 0 to infinity. So we write that, right? Then we just have to collect the like terms here. Right, so you have cn cn term here, so it's going to be, I'm going to multiply n times n is n squared, n times -1 is -n, right? So that would be cn term. There are more cn terms here. You have 4n cn, so I'm going to add 4n there, right? And also you have 2cn, so we're going to have to add 2 and a cn, right? And this minus, right? So you have a cn plus 2, so this is going to be an n plus 2 and n plus 1 cn plus 2, right? And then everyone has x to the n, right? So that's the this term right here, right? So that takes care of everyone. So all the xn, x to the n is out here, right? Set that equal to 0. All right, let's simplify. And here, this is just going to be n squared plus 3n plus 2, right? Which is the same thing as x plus 2 times x plus 1, right? So you can actually simplify, right? So we want to set this guy equal to 0. So cn plus 2 is equal to, oh actually, I messed that up again. Instead of x, this is n there. So n plus 2 times quantity n plus 1, right? So you have n plus 2, n plus 1, cn divided by actually the same thing, n plus 2 and n plus 1, right? So you can cancel those. Then you end up with just cn, right? So we have this, recursive relation, which is cn plus 2 is equal to cn, right? Then we just need to observe when n equals, starts from 0 and so on. So maybe we should do that. All right, so when n equals 0, all right, so we have C2 is equal to C0, right? And when you have n equals 1, then you have C3 is equal to C1, right? And n equals 2, right? C4 is equal to C2, but C2 is equal to C0, right? Then you're seeing the pattern here. So this is going to be, right, this is going to be C2n is equal to C0, right? And same here, if n equals 3, C5 is equal to C3, but C3 is C1. So which means that when index is odd, this is going to be equal to C1, right? So that's why you will have a summation here. Y is equal to summation n goes from 0 to infinity, right? And a coefficient is actually just a C0, right? C0 when x is even, right? And when x is odd, n is odd, or power is odd, you're going to have C1 in front, right? So that's why we have this. You can just pull out the C0 out here, C1 out here, right? Then you can see that I'll do this one, C0 summation, n goes from 0 to infinity. You have x squared to the n, and here summation, C1 pulled out, 0 to infinity, right? Then you can think of this guy as, let's see, we can probably think of this guy as C x times, right, x to the x squared to the n. So it's you have a 1 extra x there, right? So that's why here this is same thing as C0 times, right, 1 over 1 minus x squared, right? So this is a plus C1x, and this is summation is going to be just simply 1 over 1 minus x squared, right? So that's why combining them, you're getting that, right? That's it. I hope that this was clear.